I want to begin by acknowledging my collaborators and especially young people who really did all the work. So this is in particular Pavel and Ilya at Harvard, Aaron from ETH who is here, and also Shubayu and Francisco. And also there is some related work that I will not have a chance to talk about, but, including with our organizer and also experiments, and I'll mention some of the experimental results as we go along. Okay, so this is an outline of my talk. Since we will have several several talks dealing with NV spectroscopy, and this is the first talk, so I'll give a very kind of simple introduction into kind of how I think about NV spectroscopy from the perspective of many-body physics, and I'm sure this will be expanded in the follow-up talks. And then I'll try to cover 3 subjects, but so one will be how we can use NV centers to determine, let's say, symmetry of order parameters in 2-dimensional superconductors, which remains an outstanding question. Then the second one will be about seeing anomalous properties, anomalous scattering of magnons in something as familiar as ferromagnetic systems. And then the kind of final subject will be how we can use NV centers to study the kind of still unexplored phases at the transition between the Wigner crystal and Fermi-liquid phases. Okay, so for people who have not seen NV centers before, this is kind of a brief introduction. So we think about local defects in diamond, and they actually naturally spin one object, however, in a small magnetic field. And then there is a splitting, crystal field splitting between the manifold with 0 projection of the spin and ±1 projection, but then with a small magnetic field, one can split -1 and +1 states. So then for practical experiments, one is often dealing with just spin 1/2 degrees of freedom, which, let's say in this case, you can see these are states with magnetic projection 0 and -1. And this is how I will sort of think about NV centers for the remainder of this talk. And then there have been excellent recent reviews on the subject for people interested in more details. And there has been a lot of exciting work dealing with detection of all kinds of systems, from interesting kind of local objects to molecular such as like proteins and biological materials generally, and many of the pioneers such as Tono, Patrick, and Natalie are going to be at this conference, and I hope we will hear more about this subject later on. Obviously, I will not have a chance to give a decent review of all of the experiments, but I look forward to discussions that will follow. Okay, so what I will address is a very specific mode of operating NVs. And so now again, let's go back to our picture of a 2-level system. And when it is put in the vicinity of a many-body state, many-body state becomes part of the environment. And now we can think about different types of relaxation that can happen. So for example, in the kind of natural basis for the NV center, if we have magnetic field at the frequency that matches the energy difference between the 2 states, then this will contribute to relaxation, to establishing thermal population of the spin down and spin up states of these NV centers. So, and of course, if we have fluctuations of magnetic field, then they must originate from what is we're interested in magnetic field, which originate from something interesting in the many-body state. And the first of these and the simplest one is just currents, right? If we have currents flowing in the system, then by Biot-Savart's law, these currents give rise to magnetic field at the position of the envy center. And so, therefore, when we measure 1/T1, which is relaxation, right, kind of the rate of relaxation of this envy center to thermal occupation, thermal equilibrium occupation, then we can say that this corresponds to kind of fluctuations of the current in the system. And specifically, we are sensitive to frequency equal to the energy difference between these two level states. And what is even more remarkable is that this probe also has some spatial resolution. It's not just the scanning type of resolution, but basically you can think about fluctuations happening at all length scale. However, we have a very specific length which has to do with the distance between envy center and the substrate, and one can, substrate meaning the many-body state, and as we'll see later on, actually fluctuations that have the strongest effect on relaxation, they have a wave vector which is given by 1 over the distance to the envy center. Okay, so I focused on 1/T1, but there is, we'll also talk about T2 relaxation, which can be thought of as fluctuation of the field in the direction along the crystallographic axis, but what will be more important to us, that 1/T2 spectroscopy is usually operates at lower frequencies. Okay, but let's go back to 1/T1. And this is one of the simplest examples in which we can understand how this works. So this is from experiments in the Harvard group. So let's take the simplest type of kind of material, of many-body state, which is a piece of metal, right? And so we know that in a piece of metal, we're going to have Johnson noise, just, currents coming from thermal fluctuations. And as we said, we can relate currents in the system to magnetic field at the position of the envy center through the Biot-Savart's law. So this is the kernel. And now we can write the correlator for magnetic field in terms of the correlator of the current using two of these kernels. So what do we know about about Johnson noise? Well, in the simplest case, when we look at length scales which are larger than the mean free path, we know that this noise is just proportional to conductivity and temperature. So let us do some simple estimates. If we look at magnetic field correlator, then, well, roughly we are as we said, like this kernel Biot-Savart goes as 1 over distance squared, so we have to have twice this kernel, so we get 1 over distance to the 4th. We're integrating over the volume, which is roughly the same distance cube, and then we put in this sigma kt, and we find therefore that magnetic field fluctuation should scale as 1 over the distance and be proportional to conductivity. Okay, when we see this formula, it then sort of is kind of big. A natural question arises, well, what happens as we start bringing in the center closer and closer, right? Do we really expect divergence? And the answer is no, not really. So, because our simple representation of Johnson noise as something which is local in space only works as long as we're thinking about distances longer than the mean free path. And at shorter distances, in fact, the simplest way of thinking what's happening is that we take the usual Drude formula, which has mean free time, and then we simply change mean free time into the characteristic time that has to do with the time electron flies in the vicinity through this region of length d, and therefore we will see that noise will saturate. So just by measuring distance dependence of noise, one can then see a crossover from kind of ohmic regime with local relation between current and electric field to ballistic regime at short distances, which sort of corresponds to non-local relation between current and electric field. And that's exactly what has been observed experimentally in this work. Okay, and maybe just to sort of give a few details to theory-minded people in the audience. So how do we compute this like noise if we want to be more quantitative. So the idea is that we're interested in fluctuations of magnetic field, but what we can do is use fluctuation dissipation theorem. So usually the way we compute it, we think about a dipole, magnetic dipole, which oscillates at a certain frequency, and that's natural frequency of this NV center, which is around 3 gigahertz. And then this dipole radiates, and then electromagnetic waves radiated by the dipole will be reflected. And it's common when describing reflection of radiation to define two types of geometries. So this is S polarization. You see, in this case, even if we think about incident wave, electric field is always perpendicular to whatever gets induced in the material, because momentum will have to be conserved in the plane. Therefore, we expect some modulation. Like in this case, this would be X direction, but electric field is along Y. So this geometry really corresponds to electric field, which is perpendicular to spatial modulation. So this therefore will be determined by transverse conductivity. Whereas in the other geometry, this is P polarization, you can see that electric field will have component parallel to the in-plane wave vector, and therefore it will measure longitudinal conductivity. And for people who are maybe used to quantum Hall, so here transverse and longitudinal means very different. So it's because we're probing conductivity at finite momentum. When we say transverse, we simply mean that both electric field and current are perpendicular to the wave vector Q. So still electric field and current may be parallel to each other. However, they are now perpendicular to the wave vector. Anyway, so if we go through these kind of simple calculations, we will see that noise, and we can separate magnetic field noise along the z-axis or in plane. So in the case of magnetic field noise along the z-axis, you see it's proportional to reflectivity with this S polarization, which is determined by transverse conductivity. Whereas in the case of in-plane magnetic field noise, it's determined by both S polarization and P polarization. But notice, so this reflectivity in P polarization, it involves, so we said, electric current, which is parallel to wave vector, so which means that there is a divergence, finite divergence of electrical current, which means charge. And of course, long-range Coulomb interaction will strongly suppress. So if one actually goes through some simple analysis, one finds that it's usually very hard to actually extract longitudinal conductivity because it's very strongly suppressed by long-range Coulomb interaction. And primarily what's being measured is the transverse conductivity. Okay, so far we focused on noise due to kind of current fluctuation due to orbital motion of electrons, but then we can also consider magnetic noise which arises from insulating materials, especially magnetic insulators. So in this case, let's take a ferromagnet. We have fluctuations of magnetization, and we can relate these fluctuations of magnetization to fluctuating magnetic field using the usual kind of dipolar type of kernel. Then we can relate then fluctuations of magnetic field to fluctuations of magnetization. So this is from the Delft group, and hopefully Tony will tell us more about this. And also this relation, I think, was used when Yaroslav and Amir were analyzing, say, non-equilibrium states of magnets. Okay, but now let me move on to things which we have been working on, and this is, let's say, analysis of superconductors, two-dimensional superconductors. Let me first say why we think it is an important problem. So two-dimensional superconductors have been featured prominently in the last few years. They have very interesting puzzles related to them. For example, in the case of twisted bilayer graphene, superconducting phases occur in the vicinity of moto-insulating phases, and there are still debates what is the origin. Is the superconductivity driven by magnetic fluctuations of phonons, and sometimes by sort of just making a making a two-dimensional superconductivity, such as in the case of this iron selenide, one can dramatically increase Tc. However, these materials come with a lot of challenges. So like bulk probes that we're used to for regular superconductors are very hard because we have substrates. Meissner effect is also difficult to measure in small samples. And in some cases, like such as transition metal dichalcogenides, there is a big problem of even making electrical contact. So in the case of these materials, we're lacking even direct transport measurements. And this, of course, is kind of exactly where we think NV centers would be very useful, because this is a kind of contactless way of probing transport properties. In fact, rather interesting transport properties, right? So see that this transport, as we said, is conductivity at finite momentum. Now what we want to discuss is, if we look at a superconductor, can we actually see something about this superconductivity that is currently under debate. So when we talk about superconductors, as you know, the simplest phenomenological approach is to think about two fluids. One is this kind of a condensate of Cooper pairs, and it gives us conductivity that goes as 1 over omega. The simplest way of thinking about it is just a statement that if we have a condensate, it will be accelerated by the electric field. Basically, instead of Ohm's law, where velocity is proportional to electric field, in the case of superconductors, it's acceleration, which is proportional to electric field. But we still have some quasi-particles which provide sort of diffusive part of the transport. And this sort of diffusive part, lossy part, is very sensitive to the symmetry of the order parameter. But now what we can do is just take these generic formulas which we derived for kind of reflectivity of materials, and then put it into formulas for the noise and make predictions for what kind of magnetic noise we expect. So first of all, we know, again, when we talk about 1 over T1 relaxation, it must be proportional to kind of dissipative part of resistivity, right? Because if you think about physically, we have to relax the spin of the NV center, so energy must be absorbed. That's why a real part of conductivity should come in. But then, because of the interplay with the superfluid component, then we see the dependence on the distance to the surface will come with different power laws depending on whether we are close to TC, when we have a large superconducting coherence length, or at low temperatures when the gap is already large and coherence length is small. But most importantly is that the prefactor, right, this real part of conductivity, will be proportional to the number of quasi-particles. And for S-wave superconductors, it scales exponentially with the gap, whereas for D-wave, it actually scales as a power law. So kind of zeroth order prediction then is that if one measures 1 over T1, one just needs to measure noise as a function of temperature and monitor whether it goes as a power law or exponential. There are some subtleties here. So for example, if we take a D-wave superconductor with finite density of states, or say superconductors with magnetic impurities, there may be kind of other types of behavior due to nodal states. So as a test, one actually should do a much more thorough investigation, because there are more length scales in the problem, which basically have to do with the fact that we now have 3 length scales, right? So we have distance to the NV center, we have mean free path, and we also have the length, like the superconducting coherence length related to the gap. And sort of as we change parameters, including temperature, we will have different regimes which are characterized by different scaling of noise to the distance. And so therefore, I think it will be kind of a very, this will allow a fairly accurate analysis of the nature of the superconducting order parameter. Okay, now let me change gears and talk about T2 spectroscopy, and also switch from talking about superconductors to ferromagnets. So, okay, just a few words about T2 spectroscopy. As we said, it's kind of magnetic noise in the direction which is now along the natural axis of the NV center, but what is, and the way T2 spectroscopy is done, again, for younger people in the audience, we sort of bring the, let's say, basically the spin of the NV center into the equatorial plane. It precesses, but its precession can actually be modified if we have some random component of magnetic field. And what we're measuring is more or less this kind of fluctuating component of magnetic field, which again can be related to spin fluctuations. But what is important is that you notice that in order to measure this kind of fluctuating component, we have to observe the spin precessing over several periods. Therefore, we have to observe it at times which are longer than the inverse of sort of precession time. This means that we're actually probing longer times or smaller frequencies. So therefore, when we talk about, let's say, T2 spectroscopy, then rather than measurements being done in gigahertz, we usually think about kind of megahertz measurements. So it's a slower probe. But then I showed you a very simple type of pulse. People can do kind of, by now it's like an art of engineering pulses in such a way that one can really extract information about a kind of specific part of the frequency range, but again, at low frequencies. And now imagine the following situations. We have a ferromagnet, like in magnetic field. So what we know about the spectrum of magnetic quasi-particles is that there will be a gap. But kind of under, let's say, normal condition, let's say if we take not too low of a temperature, then we will see the temperature is much higher than the gap in the spectrum. Therefore, we have plenty of thermally excited quasi-particles. We have a kind of a fluid of magnons. But then, as we said, when we're interested in the kind of T2 spectroscopy, we're interested in response at very small frequency. In fact, this frequency maybe is typically much smaller than the energy difference between the ground state, than the energy required to create a quasi-particle. Therefore, if we want to probe kind of fluctuation at the small frequency, we're not really describing processes where a new magnon gets generated, but rather when a thermally excited magnon gets scattered. So from this perspective, you can actually see that this kind of rescattering processes of magnon looks very similar to measuring density-density correlation for a magnon fluid. Right? So that's more or less what we then can say, that the sort of fluctuations of magnetic field measured by the NV center will be like a density response of magnons, again, at the wave vector set by 1 over the distance to the NV center, and the frequency now is whatever, like this probe frequency that we use in our T2 spectroscopy. Okay, and now we will sort of assume that we have a fairly clean magnet, and let us sort of think what kind of dynamics would we associate with the thermally excited magnons. Well, first of all, let's just write kind of very simple hydrodynamics that should be familiar to you from basic statistical physics. So there is a continuity law, right, that we have a conservation number of magnons. This assumes that we have sort of at least U1 symmetry, and we can discuss when it's valid. And then we will just say, well, the usual equation, right, that the current is accelerated by the gradient of pressure, and of course, if we have friction, then we will have viscous friction. Notice that it's kind of very crucial that here friction comes with spatial gradients, because this comes from viscosity rather than scattering on impurity. So we assume that we have sufficiently clean system that scattering will be dominated by magnon-magnon scattering. Okay, so one can then solve these dynamics and find that response function is density-density correlation function is proportional to viscosity. Again, not surprising, it should be, okay, we're looking at dissipative part. And if we sort of take basically dilute gas of magnons, so it's like ideal gas law, pressure is proportional to temperature and density, then we end up with a statement that 1 over T2 should be proportional to the viscosity of magnons, which is quite remarkable. So, okay, by doing these measurements, we will be able to tell about actually extract magnon viscosity. Let's do some simple estimate. So if we take our basic equations from statistical physics, what do we know about viscosity? Well, it's proportional to the number of particles, temperature, and mean scattering time, which we can express in terms of mean free path. And what do we expect? Naively, we will say, oh, kind of temperature dependence will be dominated by the number of magnons. So as we lower the temperature, the number of magnons should decrease. So we should have a smaller viscosity, right? And somehow it makes sense. Well, we should have less dissipation at low temperatures when there are no thermally excited quasi-particles. But let's think about this more carefully. Okay, it's true that the number of magnons decreases as we lower the temperature. But something remarkable actually has been found about magnons by Dyson back in the 50s. He found that the mean free path of magnons diverges as we go to lower temperature. And this has to do with very unusual property that the interaction of two magnons decreases as we go to lower and lower energies of magnons. So that actually if we have two magnons with wave vectors k and p, then their scattering amplitude actually will be proportional to these two momenta. So we plug this into our expression. We find, therefore, that viscosity and therefore 1 over T2, instead of decreasing at lower temperature, should actually increase. And that is the signature of this anomalous hydrodynamics of magnons, which arises from unusual character of scattering between them. And to my knowledge, this prediction of Dyson has not been experimentally verified so far. Okay, right. So that's kind of, I would say this would be really like observation of increase of magnetic noise with lowering the temperature, Wilbur smoking, and signature of anomalous magnon hydrodynamics. Okay, actually, how much time do I have? I don't know.
Like 1 minute and 5 minutes for questions.
Okay, so let me maybe, so there is another interesting field where I think spectroscopy can be applied, and these Wigner crystals, again, I'll have to skip. So we know that there is a transition as we change, as we modify density of electrons. At high densities, we have the usual Fermi liquid. We have, but at low densities, Coulomb interactions dominate, so we expect to find crystals. And in fact, these crystals surprisingly have been observed not so, like in a completely kind of doubt-free environment, have been observed not so long ago by the ETH group and the Harvard group in transition metal dichalcogenides. What made it possible was the feature of TMD materials that they have a heavier mass and a smaller dielectric constant, which means that actually they could go to higher densities to see Wigner crystal behavior. And in this case, disorder was not as kind of important as, say, for gallium arsenide, where to reach the same interaction regime, one had to go to much lower densities, and where disorder was much more prominent. And actually, let me remark that length scales, which correspond to this density, are kind of tens of nanometers, which is a very natural length scale for these NV centers, which can sort of approach materials up to, let's say, 30 nanometers. Okay, so again, just kind of overview of results. So then we can imagine with NV centers, like either probing in the near field, meaning a separation to electrons, which is smaller than typical distance. Again, that's natural because, as we said, like period of Wigner crystals will be tens of nanometers. And in this case, the most dramatic feature will be strong spatial dependence of relaxation time, which is what we expect if NV center is right above the electron. If electron wiggles, there will be dramatic changes of the noise compared to when, let's say, NV center is somewhere in the middle of the crystal. Then these variations of noise sort of will be suppressed. Or in the far field, when distance to NV center actually gets larger than the characteristic period. So in a clean system, this would give us access to transverse conductivity, which in principle is exactly what we want to measure, because kind of a defining feature of a crystal is existence of the transverse phonon modes. And so, of course, in the real world, we do not have clean crystals, maybe just in theorist's imagination, and that's why we have to take into account the effect of disorder. And the case, what if disorder does on Wigner crystals is that it actually shifts all responses from being truly gapless phonons, like all responses sort of starts at the pinning frequency, and then it has a certain dispersion. And to make a long story short, again, by measuring distance dependence of the noise, one will be able to map out dispersion of the spinning mode, and therefore actually kind of determine the characteristic feature of disordered Wigner crystal. Okay, with this, let me conclude. I tried to give you at least a theory wish list of the many-body states that can be probed with NV centers. And I thought, okay, obviously these are not all of them, but at least some cross-section that we were interested in, including superconductors, magnons, and crystal states of electrons. Thank you.